write it in English first, and once you write it in English, then the rest becomes easy. The hard part is writing it in English. The hard part is not the design. Once you write it in English, you identify the sequential elements, you identify the combinational elements, you mark them up, and then you connect them appropriately. But if you have to write English, it's kind of the rest of the process is trivial. So the hard part is writing the correct English to get all the data paths. Okay, we did not do the control path last time. So how do we do the control path design? The very first thing we do is we identify all the control signals to every single unit. For memory, for sequential elements, the control signals are basically the write control and the read control. Here's the read control, here's the write control for a memory, and similarly for a register, they have a write control. We don't need a read control. We'll talk about that in a few minutes. And then for every mux, you have a mux select. And for an ALU, you have an ALU opcode. So basically, you have all these control signals, and we identify all of them. In the book, the control signals are all in blue. So we have all these control signals, and they're all, well, when I say tie them, I don't mean literally tie the wires together. That was just quote a chip. But we bring all the control signals and make them an output of the control.
God forbid someone's niece.
So now we have to decide, we have to figure out what actually goes into that control block. It's going to be a huge combination.
Yo, I forgot the piece of
but we don't know what it is yet. So that's what we're going to do next. Everybody good? Everybody knows what we're doing now.
You left
for
the
the rest of the way today.
Before
Okay, so what we're going to do is we're going to identify all the paths. So first we're going to do R-type.
Oh, it's acting like he gets this.
So what is an R-type instruction? It reads two registers. It sends the two registers to an ALU, for example, an add. So that means it has to get this input to the MAD has to come from this input to the MUX, not this input. What does it do with the result? An R-type instruction, the result goes back into the register file, and it goes into the write data. How is it getting there? Okay, and this MUX, you don't want this to get there. You want this MUX going there. So going there, going there, going there, going there. So that is the path executed by the R-type instruction. Change colors. Okay, let's do load word next. What are we doing for a load word? We're getting a register and adding a sign extended immediate. Where is the sign extended immediate coming from? If you remember the machine code, it's bits 0 to 15 of the instruction, so that's the immediate. You want to do a sign extend to make 32 bits. And we're adding that to, if you look at the machine code, bits 25 to 21 of the instruction contain the register that is the base register. So the base register is in bits 25 to 21 of the machine code, and the immediate is in these bits, 0 to 15. So we add them together. So we bring the base register here, we bring this immediate here, we add them together.
Huh?
And once we do with the
That's the graph from last
what is
time,
the
remember?
result of the load
They're
word?
rad.
The result
The
is
orange thing is the R-type instructions. The green one is the
It's an
process of a
address,
load
yes.
word.
It's an address that goes into the data memory. And then, so we're going to be reading that memory. And where are we sending that result? That result is going to go back into the register, into the destination register.
Jesus Christ.
Okay? doing is we're looking up the machine code, and I mean, obviously we picked the machine code to make sense, but we're looking up the machine code and finding the paths that are executed, that are exercised here. And also, as an incidental side effect of all we're doing, remember, if you thought about it closely, you would have noticed that, not a whole lot of thinking, you'd have noticed that we never really said what happened to the decode. Because what is decode? On a RISC processor, decode is trivial. It's basically breaking down this instruction into all these fields, which is not really real hardware. It's just taking these 32 wires and sending them into different places, sending some subset of them into different places. So the decode is basically this stuff between my hand and the pen. It's trivial. I shouldn't even cover the control. That's the decode. I shouldn't even cover the mux. That's the decode. So that is trivial, which is why we didn't really talk about decode. Once we did the rest of it, we just looked up the machine code and said, yeah, I need bits 15 for 0 coming here, and bits 20, whatever. That's just a matter of looking things up. Okay, let's do store word next. Store word, the first part of store word is the exact same as the first part of load word because it's still computing the address. So store word, maybe I'll do, actually I'm going to do store word last because I don't know how many colors I have. So next let's do the jump. Okay, what is the jump? You have this 26-bit field in the instruction. Oh, I'm sorry, not that one. Do not copy that one. That's an error. Okay, sorry about that. I'll change the color of that later. Yeah, the 26-bit field for the instruction. You shift it left 2. That's what we did when we did for jump. Remember, jump is an absolute address which we it's an absolute word address, so we have to multiply by 4, which is the same as 15. We also have to append, that gets you 28 bits. How do we construct a 32-bit target address? Is we take the upper 4 bits of the PC and append it to that. Upper 4 bits of PC are coming from here. And that gets sent back into the PC by going to these muxes.
Where did he get the picture from? He uploads to MySpace.
And that is basically the jump instruction. We're intentionally doing branch last because branch is a little weird. Okay, let us use let's use yellow for let's see. No, let me do it this way. So it's a store word. I'm going to get the always store word part 1 is already covered by load word. So store word part 1 is already covered. Store word part 2 I'll do in pink. Okay, because the store word part 1 is just computing the address, which is the same as for load word. So store word part 2 is, you have that, no, I shouldn't do that. Let me do the, no, forget it. I'm not going to break it up into parts. Let me do the entire store word again. So store word. So everything in green is still there. You do the immediate sign extend. You add that. So you compute the address. Except now you're not sending data. I'm sorry, you are, in load word you are not sending data. For store word you are sending data. So if you look at the machine code for store word, magically, well not magically, you'll just mark by picking that machine code. Bits 20 to 16 of that machine code for the store word happen to be the register that you're reading from. gets read, and that gets I'm sorry, I made write this down. Okay, the black is the strikeout. So the store word goes down here, and it goes into the write data of data memory. So that you're sending the data, and you're sending the address. Because that's what a store word is. You're taking a register, which is selected by bits 25 through 21. No, it's selected by bits 20 through 16. And you're computing an address, which is the sum of bits of the register selected by bits 25 through 21, and the immediate sign extended. That's the address. The data is the register selected by bits 20 through 16 of the machine code, and you're doing a write. And this green part does no longer appear because you're not reading the memory, you're only writing the memory. So that's a store word. Okay, what's left? We're not going to do branch stuff for now. But what is left is fetch. I guess I will have to use yellow for fetch. Okay, what is a fetch? All it does is it takes PC and it does PC plus 4. So and PC plus 4 goes into this mux.
Damn, 5 colors.
And that goes into this mux.
You think he
And
takes notes in
it comes
Sharpie
out
too?
here.
In what? You think he takes notes in Sharpie too?
Okay, so that is the fetch. Again, we're going to do branch later, but for now, we're going to figure out the control path for these instructions. Yes? How do I what? Because that's what we designed last time. Because to get PC plus 4 back into the PC, that is the path you have to take. Because you want this to get back into the PC. And that means you have to go into this. The only way on this data path is to take these two mux inputs. You have any other way of doing it? No, the answer is no. Oops, let me put it. Okay. So now we have to do the control path. So how do we control all of this thing, this mess? The way we do the control is by we have to select. Well, it's more than selecting the mux, but to a large part, it's about selecting the appropriate control signals to the muxes, and then you have to select the control signals for the memory. So you have to give 0, 1 values for all these control bits. Let's do it. R-type, orange. Okay. Red desk. What is this mux? Well, just see what's orange. That's a 1. So I'll write it right next to here. That's a 1. Jump mux. That is this mux. For an R-type instruction, we're doing a fetch. We're not doing a jump. So the fetch is a yellow. So we want this mux to be a 0. This mux, we want it to be a 0 because we want the yellow again, fetch. Are we doing a memory read for an R-type instruction? No, so that's a 0. Mem to reg, this mux, what is it for an R-type instruction? Is it a 0 or a 1? Actually, it's a 0 because it's an orange. Yeah, you got it right, but some people said 1. So it's a 0. ALU off. Okay, I'm going to do the ALU. Yes.
The one under jump is branch, or fetch.
Let me see. Did I screw up? No, the yellow is a 0, because we want fetch. We haven't done jump yet, we're doing R type. So we want fetch, which is a 0 and a 0. Did I, oh, I did
Oh,
write
wait, these
0
are
and 0.
all for, okay, wait, I got what you're saying. These are all for when we're doing a R type.
Yeah.
What is an R type? What is an R
Okay,
type?
ALUR.
Register type.
For
What is the other one?
ALUR,
The
I'm going to do something slightly
for
different
I-type,
in the
yeah.
book.
Yes,
Because what
R-type
the
and
book
I-type.
does is they do
Yeah,
some
right.
additional
R-type
level of
instructions,
decoding, where in
I-type
ALUR
instructions,
gets
there's jumps.
sensitivity here, and you do
There's
some
memory
additional
instructions
decoding.
like
That's,
those.
that's primarily an implementation detail, which I don't really care about, because that's very specific to this implementation. So for ALUR, I'm just going to write, what am I going to write? I'm just going to write, for R-type instruction, it's whatever op that bits 20, bits 5 through 0 of the instruction select. I don't care what value, what 0, 1 values those are. So I'm just going to write op. And I will expect you to just write op. That's making it life easier for you. Otherwise, you can look it up in the tables, which is just mindless work. There's not much point to it. Because for an R-type instructions, the operation you do in the ALU depends on what exactly that ALU op is, which is dictated by bit 0 to 5 of the instruction, which is coming through here. So, so the details of what actually happens is there's some combinational logic which interprets bits 0 through 5 of the instruction along with this ALU op field and produces the appropriate ALU op. But we're not going to worry about it. We're just going to write op. Okay? Memwrite. Are we doing a memory write? No, 0. ALU source. That is this mux. Is it a 0 or a 1? 0 because it's orange. Yeah. Reg write. Are we writing the register file for an R type instruction? No?
Yes.
Yeah, we are. That's the whole point. Because we're adding, for example, we're adding 2 registers and storing it in the register in some register. So we are doing the reg write. So that's a 1. Yes.
Wait, why is the first one 1?
You mean the top one at the top, reg def?
Yeah, when I follow the path, there's no orange.
Actually, there is. This mux asks. This mux, you want to select bits 15 through 11 of the instruction. That's orange.
So is the path,
This path is going down here.
and it's going into the box?
Yeah. It is.
Where's that orange?
The control is going into, this is the control coming at the bottom. The data going into the mux is part of R type, is indicated in orange.
Okay.
So we want to make sure that the orange data goes in and not the green load word data goes in.
Oh,
Because otherwise you're picking the wrong register.
Isn't that better?
okay.
Actually, to clarify, maybe I should extend this green to there.
Other clouds, especially 265 and 260.
I mean, it's the same thing, but because your question indicated that it might be true.
You gotta be
I mean, there's some things that we optionally can include or exclude,
Let's say not to be nice.
which, depending on questions, I might
Awesome.
add that. Is there another question?
Okay, C plus
Sure.
minus to C plus
I mean, it's a good time to ask questions.
somewhere there.
Okay, so we did the R type.
Yeah, we're going back to
Now, one thing I want to mention is, before I go on, is
we're
the
both probably
register
not seeing this
file
one.
only had a write control. It did not have a
So I
read
think it's a
control.
tool.
Because normally for sequential elements, we don't really need to explicitly say read it. Because if we're reading it into these wires anyway, we just ignore it if you don't want to use it. There's no point in having an explicit read control for sequential elements. Which is why the register file does not have a, has a write control, read write, but it does not have a read control. However, the memory, remember, is ignoring cache. It's going to be off chip. So it's nice to have an explicit read control for the memory because that indicates that it's off chip. It's going to be used by other things. For example, one of your homeworks was a robot that directly accessed. It didn't. Well, it was not real memory, but let's say it is. It was directly accessing memory. It's possible that other I/O devices directly access memory. Your project you drew yesterday is essentially directly accessing memory because you have to display which is yanking stuff from the memory. So it's nice to know that I'm not beside the CPU, I'm not using the memory, I'm neither writing nor reading. So other units, I/O units, memory managers, they could use the memory. So for the data memory, you have both the write control and the read control. Just, because otherwise you have to waste time for that, because they don't know if you're using it or not, and two
Yeah,
people
I'll
can't
probably
be
check this
using it
out
at the
then,
same time.
because we're still gonna look for
So the data memory is an exception, but normally we do not have read controls for sequential elements. We just say we'll just ignore what you're producing. I mean, if you say something and my ears are closed, it doesn't really matter what you said, right? We're always reading the register file. ALU will just ignore it. This mux will just ignore it. This memory will just ignore it if it's not controlled appropriately. Okay, so that's
This is pretty
read
cool.
word.
It's a rotation
I'm sorry,
of
art
like 5
type.
years.
Now let's do
And then you can choose pretty much whatever you want to do.
load word.
Will they sponsor my ads?
Okay, load word.
Oh, what? Man, my photos are really cool.
This mux
Or I can
for load word is a zero.
use my OTP.
Jump mux, well, the jump mux and the branch mux, those two are still doing a fetch, so they'll be the same as the R type. Yes. Mem read, are we doing a read for the load word? Yeah, that's exactly what we're doing, so that's a 1. Mem to read, that is this mux. This mux is 0 or 1 for the load word. Yeah, 1, green, yeah. ALU off. What are we doing in ALU for a load word? Well, we're not doing some arbitrary operations. We're doing something specific. For a load word, what are we doing? We're taking a register and then sign, extend, and immediate. What are we doing to those two? Yeah, we're doing add. So let's try to do this. Plus. I might sometimes write ADD instead of plus, either way. Memwrite, are we doing a write? Memory write for a load word? No, 0. ALU source, this month, good, 1. Read write, are we writing the register file? Yes, 1. Okay, so we got the load
Should it
word.
be 0?
Yeah. Yeah.
Yes. According to the green line, it should be the mux input is 0.
Which mux input?
The one on the left, the one to right register.
No, that is the green line. Oh, yes, that is a 0. Yes, you're right.
But is that
We're looking at
different?
that other mux.
Are you looking at this mux?
Yeah.
Okay, so this is a 0, and this is a 0.
Oh, okay. So red right is the one coming from
Red right is this one. Red right says do the right. So I have a well, red left says that it's called REDST. That's saying pick this element. I'm sorry, this is not that. I know this is not the best that the focus will give, which is why I told you to print the pictures out. Yeah.
Are you free
Did I answer your question?
Yes.
Okay.
Are you free Tuesdays as well?
Can you
Are you on
say
campus
again
Tuesdays as well?
what else
Yeah.
ALU
But I,
Because you're through Tuesdays, right?
Tuesdays and Thursday I cannot because I study for 265.
Oh, ALU off.
yeah,
ALU
yeah,
off.
that's
Just,
for sure.
remember, the ALU has like, let's say it has 32 functions or 16 functions. I don't remember exactly how many it has. Add,
I can every single
and,
Friday
or
except
whatever.
tomorrow.
Instead of memorizing that and happens to be 0, 0, 1, whatever, I'm just saying
Yeah.
I will write either plus,
Yeah,
minus,
are we gonna get
off,
something
which
out
is
of
I'll tell you about that in a second.
I cannot.
I'll write either
Thursday.
plus, minus, or off, or don't.
Tomorrow I need to study.
Now, what is off? For R type, there are many different R types. There's the AND, there's OR, there's add, there's subtract. Each one of them corresponds to some different bit value on the ALU off field.
is shift right logical and shift left logical also an off?
I'm going to lie and say yes. Do you want me to tell you why I'm lying?
Why would he?
Okay, but this will only confuse you more.
Look at my
okay,
professional
in
man.
practice, shifting is a pain. Shifting by an arbitrary number of bits is a pain in the hardware. So what we often do is we have an ALU, and right next to the ALU we have something called a barrel shifter, which is explicitly for shifting. And so we would have an ALU here, we would have a barrel shifter here, and we would complicate this diagram and send stuff to both ALU and the barrel shifter, and have another mux that picks one of them to get for the one we really want. But as far as this course is concerned, we'll just assume that shifting is another ALU output. But it's not available. But we want to keep our diagrams manageable. Yes?
Is the control unit, the control element, is it just like a decoder?
Yeah, let's talk about that later. Yeah, let's talk about that later. Okay, let's do jump. Okay, jump. What is this mux for a jump? 0 or 1? Why? Do you see a blue coming into the 0? Okay. Yeah, well, it could be either, it doesn't matter. So that would be a don't care. Don't cares are indicated by X's. Now, if you remember, well, you do remember 160. If you have a don't care in a Karnaugh map, that allows for a lot more logic minimization, because you can interpret it as either a 0 or a 1, and you can optimize it. You can do the Karnaugh map minimization for whichever one makes it smaller. So you can interpret the X as either a 0 or 1. So we, the hardware, the CPU designer, you just tell the VLSI designer, I don't care what that signal is. You do whatever you want to make it more optimal. Maybe making this a 0 will have fewer gates. Maybe making it a 1 will have fewer gates.
Don't
I'll
say
leave it
much,
to you.
but just,
I'm not going to
because it still
overspecify
feels
my
unreal at
system
times.
because I don't need to. Because I really don't care.
What?
Okay?
Why are you showing me this?
The
No,
jump
I was just saying,
box.
like, anytime I get the signals, I always like kind of
Because
That
I
box
sent
is
you a
going to
picture of
here.
a real dog called me.
So instead of 0 or 1,
Because I remember I sent you
yeah.
a real dog called me.
Which one?
The branch
And
mux,
the system is going to make it an intention.
that mux is going to here. Is that a 0 or a 1? Yeah, that's a don't care because it doesn't matter what gets sent here because we're going to fix this one anyway. That's a don't care.
Wait, where?
The branch mux. Mem read. Are we doing a read? 0, 1. Don't care. Okay. Well, if we the don't care here is not the right answer because remember the point of the mem read is that we want to let the memory your system have freedom to read the memory. So if we have it don't care, then we're saying I may or may not read the memory. So we're the VLSI designers, they might design it so that you are reading the memory. In which case you're reducing the functionality of the system, the performance of the system, because you're preventing some other unit from reading the memory. So we want to explicitly specify that we're not reading the memory.
Yeah, originally he's her pet, but then
0.
she's kind of irrelevant, and
Mem
so
to red.
like the
This
writers knew
mux.
that too. And so there was
That's a
a
don't
whole
care,
chapter
obviously.
/ volume about her giving him to
ALU
Deadpool.
off.
So now he's
What are we
Deadpool's
doing
pet.
in ALU for a jump instruction? Do you see any blue here?
That's so cute though.
Don't care. Mem right. Are we doing a right?
They did
Does that
such a,
mean 0 or
they did
don't
such a
care?
good job with her character selection.
0. Good. Nobody says don't care. Don't care is wrong because then you might accidentally write some whatever happens to be the bit pattern on this address. You might be writing that location with whatever
yeah.
the
Flush it or
this
something, right?
pattern on this data is. So you want the mem right to be 0, not a don't care.
Okay, so this one should be a don't care.
What?
Why should it be a don't care?
For mem right, you should almost never be a don't care.
Okay.
Because I mean, either you're writing it or you're not writing it.
I don't want to feel stupid that I'm not paying attention, so I'm going to study on that.
Well, if you don't care, if you don't, it doesn't matter which one you do. In general, for combinational elements, it doesn't really matter.
That's not mine, that's
But
yours.
for sequential
Timing.
elements, it does matter that you're not writing some random location in memory or with some random value. Or a random register with some value. Okay, let's finish this. The ALU source, that is this month, doesn't matter, no, don't care. Red right, are we writing the register file? No or don't care?
Zero.
Zero, good. Same reason that mentioned before. Okay, so that's still jump. I think we have to do a store word next. Okay, store word. What about this month? 0, 1? Yeah, don't care. There's no pink here. Store word is not, we don't care which register we pick to write. We don't have to be writing the register anyway. So that's a don't care. The jump, well, that's going to be the same as a fetch. So that's going to be 0, 0. Mem read. For a store word, are we doing a read?
Oh no.
Yes.
Why is jump and fetch zero instead of don't care? Is that
Because we want to do a fetch. Because we want to advance to the next instruction. If we make that a don't care, then we're jumping to some arbitrary location, some arbitrary instruction somewhere.
okay?
Which would not be a good idea.
Okay. So we have to like follow the flow chart, but we also gotta think about it.
I guess. I mean,
Well, if I just follow the rules of following the flow chart, I would have put a don't care.
He said the same thing.
whatever.
He said the same
Oh,
He said the same thing.
Yeah, for anything that's not branching, you need to
He's listening
do
to
a
our
fetch.
class for us.
Because you're going to the next instruction. The reason I did fetch separately is because I didn't want like every color on those lines. Because that would make past experiences, that just makes it more complicated. Okay, so mem read. Are we doing a read for the store word? No, that's a 0. Mem to reg. Do we care? No. ALU off. What are we doing for the ALU for store words? What?
Supposed to be.
Yeah, you want to add. Yes. So you're doing a plus. And for mem right, are we doing a right for the store word? Yes. 1. ALU source. Yeah, you're doing an add, so you want to get source for that. Just looking at this, it's pink, so it's a 1.
that's doing something important.
What? Oh,
You have the textbook?
thank you.
Did you buy it?
No, I found it. In the thing.
Red right, are we
I
writing
found
the
this one
register
in
for a
my
store
phone,
word?
one of the, I think,
No.
beta
Some said yes, some said no, but
You're looking at it.
no, I want to
not to the right
I
register.
want to use it.
To take it back?
Yeah, exactly, because it goes all the way to.
Okay, so
Oh, you can use it to
including the
review after,
branch,
'cause it's really
we
good.
are complete with the control
Yes,
path.
but there was someone
And
who
we're
said
going to
at
do the
first
branch
Chinese.
But we're complete with the control path. So what do we do now? We take all these
So I'm
symbols that we just
inheriting
figured
our-
out, make a table out of it.
This Chinese girl probably got it in her class, bro.
That's the table.
You think she left a number already?
I'm not going to zoom in because it's just a bunch of ones and zeros and X's. You can look at it. It's a bunch of ones and zeros and X's that capture what we wrote in the previous
That's pretty good
diagram.
review though for it.
So what do? You all have taken 160. So you make a big truth table out of this. How many inputs does it have? How many outputs does it have? Each column is an output. So there's 1, 2,
And then
3,
you can
4,
start
5,
to see
6,
like
7.
there's just more
There's
reviews
8 plus
than
the
to get a
ALU
file.
op.
And
ALU
then
op is
this is
actually
like, it goes
like
really
3
in
bits
depth
or
further
4
stuff
bits.
into the file.
I don't
Takes
know
4
this
bits.
hashing, I don't know
So
anything
so
about
we
hashing.
actually have it's a call out test.
Hashing is 335.
How many inputs are
Yeah,
there?
but it's easy.
All
You don't
these
need to
inputs are
do it understand
determined
the nearby stuff.
from
So have
this
to use hash
5-bit
tables or
field,
dictionaries.
5 or 6.
That's what hashing is pretty much. So it's pretty easy. But the implementation for hashing uses
It's actually
and
6.
stuff like that.
26 to bit, 26 to 31.
List.
So that's 6 bits. So you have 6 bits in the machine code, which are the inputs. So from those 6 input bits,
Well, it starts with T's.
and 12 output bits, you make a huge truth table. You know how to do that. I'm not going to do that because it's huge. But you can do that. Then you can apply all the techniques you learned in 160 to make some big combinational circuit, some of products, combinational circuit with AND gates, NOR gates, and whatever else. And that is exactly, and that circuit is what goes in here. So some huge, a bunch of gates goes in here. And now, exploring the branch instruction, we have now completed a
What
CPU.
old notation is this one? What old notation is this
Get
one?
up, stand on top of your desk and celebrate.
For I and branch major equal to 0. And
Okay,
again
now we need to
for
start
I
talking about
and
branch.
branch.
The reason I
wait, was it
delayed
the
talking
same?
about branch is because branch
different thing?
is kind of in between. I think we do the data path design
No,
and the
it's
control
plus
path
I.
design.
Oh, my bad.
So
I literally.
the problem with branch is that the data and the data and the control is tightly linked together because whether or not you do a branch depends on the data. So whether or not you do the branch is kind of control-ish, and but it depends on the data.
That's so right, this is all square because
I'm
this is
here only
two
to branch and equal.
Yeah,
So it
exactly.
depends on whether they
That's
can
all
get
one
the
square because
two
it's just the
registers
biggest one.
so that kind of mixes the data path and the control path, which is why I
Where is
put that
called?
class. So I'm not going to mark this up because I'll just make a
Try
mess.
this.
So I'll just show you what happened, and I'll get a fine point. Here's a fine point. Okay. Well, maybe I'll use my purple C. Yeah, this black pen should be a branch. Okay. No, black is, it's already in black. No, I don't want to use black. What? Yeah, but it's gonna get confused with this black. Maybe I'll use my purple ink. Does that look different?
Yeah.
Okay, so I'll use my purple ink. So what is the branch? You're reading two registers to compare them. We're doing a branch and equal. Yes.
Yeah, I can't find it. I was gonna test it on something, but to try to see if it's all volume or not.
What is chat saying? Oh, is it repeated?
Okay.
There's that picture.
Sure.
And we're checking if they're equal by doing a subtract and checking if the result is 0. And if I'm going to ignore this AND gate for now. If the result is 0, what is the address we're branching to? We're taking the 16-bit field. Yes, but the label was computed. If you remember, the machine code is a PC relative word address. So we're taking the machine code with 0 to 15, sign extending it to make it 18 bits and convert it from words to bytes. I'm sorry, sign extended to make it 32 bits, then to shifting the left 2 bits to convert from a byte offset to a word offset, because we want to multiply by 4, and then adding it to the current value of the PC. Actually PC plus 4, but let's. And this is going to go, and that is computing the target address. Again, we're taking the 16-bit offset, sign extending it, change it from a byte offset to a word offset by multiplying by 4 or shifting left 2, adding it to the PC because it's PC relative.
Oh,
It could be a negative number, so
Yeah, why
you're
not
assigned a 2 complement. So it's,
You got
you're
it.
adding either a positive number or a
I'm
negative
getting
number
it.
to the PC. And you send that back into the PC.
Those are those. This is our position of putting
Actually, the purple kind of works because the yellow is kind of a highlighter
This is
on
the
top of the purple.
Actually, I try and avoid.
So that is, okay, I kind of ignored this, the AND gate. But that is the basic data path for the branch. So now I'm going to talk about the AND gate if there's no questions about that.
That's the only time
The
I
basic
have been
idea of the
successful
branch is
in
that
the
there's 2
application
parts.
tries to
One
say,
part which is comparing the 2 registers and getting the
There's a
0
really
result.
offensive
You
one thing
subtract 2
about it,
registers and
yeah.
check if it's 0, you're checking if it's equal. And the other part was in computing the address. Now, how do we use this to determine which address? Because you might get the computed address, but you might do the PC plus 4 if you're not doing the branch. So we have to get the PC plus 4 also. equal, excluding PC plus 4 side. Okay? Because I don't want to mess up the diagram. How do we do that? If they're equal, this is going to be a 1.
These are hard to find.
So if they're equal, if the one input of the AND gate is a 1, that means the other input of the AND gate gets
Please
true.
I'm not bugging.
So if they're equal, the branch control will get true. And you'll pick, we'll make it pick this input. If it's not equal, this is a 0, which means the output of this is a 0, which means you will not be doing the branch target address, you'll be doing the PC plus 4. So that is how they use the result of the register comparison to decide whether we're doing PC plus 4 or the branch target
It's
address.
a bed amongst time. You have to watch it. I don't mind.
The singer that shows up in Piper's video, that's a good range.
No, if the 0 flag is a 1, that
The
means
girl
it's
shows
equal.
up in Piper's cover video, she's a good range, she's from the time.
Yeah. Yeah.
Where did you see that?
And so that is how we bring this in. Instead of messing up this diagram, I'll just stop, throw out this figure again. And this, the second row from the bottom happens to be the branch unequal.
I don't know the name of that one.
And let's see, and the ALU off now is a subtract because we're subtracting the two registers. Okay, so if you look at the purple from the previous, the purple ink from the previous slide, that corresponds
No, I think
to the
it's
second row from the bottom here. I know this is not terribly readable, but you have it
What kind
on,
of name do I know?
you can print it, you can print it. It's a bunch of zeros at once, it's not terribly exciting. So again, we just made the truth table a little bigger, but it's there, and that is all there is to it. Yes.
One of your inputs into your AND gate comes from your ALU. Where does the other input come from?
The other one is coming from the branch control signal. And we're going to say, and the branch unequal instruction, that's going to be a 1. So basically, this the one coming from the ALU is basically either disabling it. If it's a 0, meaning it's not equal, it's going to say, I'm never going to do the branch. It's going to ignore the branch control signal. If it's a 1, I'm just going to say do whatever the branch control signal
Hell
tells
yeah.
you. It happens to be a 1.
Oh yeah.
Okay, did I answer
Me
your
after I
question?
saw my 335 score.
Any other questions? Yes.
I'm not gonna be yes when I get to my turn.
By default from our control, whenever we do a read register, write, or a save word, we are setting a 0 to the end. And if we're not using,
Well, I think I know what you're going to ask. Because if this mux is going to be
1.78
a
version.
1, it really doesn't matter what this mux produces.
1.78.
This is why this mux
70 or 1.7?
1.7.
was an X. Oh. Yeah, no, there's a 0. No, hold on. For R-type orange,
Okay, bro, yeah.
oh,
Oh, that was last week.
I should have made this mux an X. And I should have made it an X. But however, I'm not going to change it because the diagram I have does not cut it as an X.
One? That's gotta be a day.
Well, actually,
Yeah. There's gotta be.
I'm not sure if
you?
I believe I got this from the book, so maybe the book has a typo
Yes.
in it too. Well, it's not a typo, it's just not as optimal as it could be. So let's not worry about that because that's just not implementation.
I'm charmed, you?
Other questions?
I don't follow my taxes.
Okay, so now we're have to distribute the tests. Okay, you want to listen closely. Don't talk, you want to listen closely. The height score is greater than the usual ABCDF scale. The height score was a 3.8, which is very good. Now, I do not make curves on individual tests. the end of the semester. But if I were to make a curve based on this test, I would say that if you got over a 3.02, you're in the A range. If you got between a 2.12 and a 2.98, you're in the B range. The high end of that could be an A minus. If you got between a 2.00 and a 2.08, you're in the BC range, and you could be borderline. If you got between a 1.5 and a 1.98, you're in the C range. If you got between a 1.4 and a 1.5, you're in the C range, but you better watch out. If you're below 1.4, you really have to watch out. And I will say that the majority of people tend to go down in the second half and not up. Very few tend to go up. It's not because the second half is harder. It's because the second half relies on your knowing the first half really, really well. So